My two favorite students.
Hey, Bill.
Brendan,
How's it going?
excellent. How are you?
Yeah.
I haven't talked to Stephen Freeze in a while. We did like an hour this afternoon.
Oh, geez.
Yeah.
Getting them all day.
There's Stratocaster.
Switching up the scenery, huh?
I know. You ready to play today, Stephen? Hey, Sean.
Hey, Bill, how's it going? Happy New Year. I don't think I talked to you yet. Happy New Year.
I know. I keep putting meetings when you're working.
I know. I know. I was 2 for 2 with you. Sorry about that.
Yeah, my fault. I had a slow start to the year, just trying to get my bearings. I don't know. Vacation was really good. I don't know.
Well, that's a sign of a good time off. Nothing wrong with that.
Yeah, but it took me like a few days to get my pulse back. I know Daniel's going to be late. He sent me a text because he's driving home from Light Meadows, and I think Roy will be on in a minute. Andrew had to go to had an appointment, doctor appointment. So I'll have the video anyway. Hey, Sergio. Hey, is that Carolina or is that Connecticut?
I assume by the open door in the background, it can't be Connecticut.
Brandon is correct.
Nice.
Sweet.
Sweet.
Well, the good news is I'm excited about today's class because I had a month to work on it and revamp it. And I did some of it in Florida and not a ton of time, but I'm excited. Can't wait to see what you think. Because I think
we can take a month between all the classes, right?
Oh God, how nice would that be?
Take us 3 years to get through it.
I mean, my college classes, I'll change it on the way there. Daniel de Mendoza could tell you, I'll change my slides. Like, it's continuous improvement. So I think I'm going to maybe give Roy, maybe I'll start. Okay, guys, because I am recording this, just the FCC guidelines. I have to tell you, I'm recording it. Everybody see all right?
Yes.
Right. So where we left off, we finished off define and measure. Measure is what do we need to improve? Can we measure this? Kind of a big version of the current condition in the A3 form, since I have all Olbrich people here. And today we're going to start into analyzing the process and define factors of influence. Can we make the data scream at us, talk to us, because data just lays there. And it's about finding the top, remember the formula Y is a function of a bunch of 3 or 4 X's, those few vital factors. If I have a whole bunch of data laying on a piece of paper or on my computer screen, it doesn't necessarily scream at me, what do I need to look at? What do I need to improve, which is the next phase. So it starts with team input regarding potential causes. Again, data by itself is one thing, but you need the team too, the experts, the people doing the process to kind of give you some insight, especially as we get into some hypothesis testing, which is part of the analyze phase. We can't let go of that human, the expert. And then I'll teach you some statistical methods, some guys, be reviewing them to help isolate those top 1 or 3 causes. Today, my plan is to get through multivariate analysis, different classes of distribution, a little bit of inferential statistics. We're going to play a little bit of practice with that on the math practice spreadsheet that we've been working with. And we're just going to get into hypothesis testing a little bit, some basic concepts of it, 1 and 2 tail tests. And we're going to stay with hypothesis testing next week and the week after for the most part, because as you can see, most of the analyze phase is all these different types of hypothesis tests. All right, and I mean, I'm not going to cover each one in detail because I think, most of the time you're going to use 3 or 4. Now it's just a matter of understanding what they all do. Why would I do different tests, things like that. But it's all the same theme. The theme is make our data scream, talk, because it just lays there. All right. I was telling Steven today, one of my mentors, my first mentor out of college was a chemist, and he said to me, Billy, data is like a bikini. What it reveals is interesting, but what it conceals is vital. So I think this analyze phase is, it's about making good decisions, being able to make predictions. Here we go. And again, these are all just hypothesis tests with non-normal data. So, the next 3 today and 2 more weeks, we're going to kind of just chug through a lot of hypothesis testing, except for today. So let's start with patterns of variation. And I think this is a really simple tool that you may or may not have been exposed to in the past. Multivariate chart. Are you guys familiar with that at all? And it kind of goes against every law, every rule that I've ever learned as a chemist, as a researcher, or as a, it's graphically, multivariate chart, it displays patterns of variation. So I got all this data that I've collected and I have a sample of it, or maybe I'm looking at the whole population. But there's certain families of variation we're going to talk about, three types. Here comes Daniel. I don't want to go too far without that kid. Daniel Mendoza.
Hello.
Made it.
Yay.
All right, could you see the screen okay?
Yeah.
All right, I'm going to back up just a little. I'm going to go real quick, okay? So we're in the analyze phase. We're done with define and measure. Today we're going to cover patterns of variation, inferential statistics, and we're going to just kind of dip our toe into hypothesis tests. All right, and again, the theme of analyze is making our data talk to us, scream at us. Because it just lays there, otherwise it just stays on the paper or on the computer. And we just started, this is where we just left off with patterns of variation. There's 3 patterns that the variation that I see in my process and in my data, they kind of all follow these 3 things. And there's a tool called multivariate chart, which I just said it goes against every law of I ever learned as a chemist or a researcher. So I'll tell you why in a second. So as a tool, multivariate graphically displays patterns of variation. So all the graphs that we talked about in the design phase, whether they be bar graph, histograms, run charts, control charts, they're all doing the same thing. They're trying to make our data talk to us, because again, it just lays there, doesn't talk. In this particular graphical tool, it looks at a whole bunch, maybe multiple variables at the same time. That's the beauty of it. I'm going to give you a real world example of it. But variation, there's 3 classifications of variability in our processes: positional, cyclical, and temporal. So positional means that I have variation within the same unit. All right, it could be within a piece, it could be within an assembly, or a unit that contains many different parts. It could be a location in a batch, for example, in a plating process, where I pull out a piece and it differs from another piece that's in that batch. So the first source of variation, and a lot of times this could be due to our measurement system, where we talked about gauge R&R in the measurement phase, but maybe we have 2 operators measuring the same piece and they're getting different numbers. It could be I grabbed the wrong test instrument, the one that hasn't been calibrated, or the calibration fell out of it fell out of sync. Okay, but positional means within the same unit, and cyclical means between consecutive pieces, not the same piece or unit. It means I have differences from piece to piece. And then one that I think is pretty obvious is the temporal, which is over time, where, you know, depending on, I might get differences shift to shift measuring, day to day, week to week. Okay, so those are the three types of variation. A real world example of this is, let's say my wife and I were crazy enough to want to open up another yogurt shop. I'm not saying I'm crazy enough. Maybe Gloria, she's the one doing all the heavy lifting. But let's say she said, hey, you know what? I'm thinking about opening up another yogurt shop. And there's a few variables, you know, that I would want to look at. And the reason I say that multivariate analysis, it goes against a common principle, you know, in research and in my career as a chemist, is that I only want to change one variable at a time, right? I don't want to be looking at different, I want to make one change at a time, you know, measure that. Single factor experiments, you know, even when we talk about A3, we're talking about single factor experiments. We're not looking at a huge number of things that, you know, variables. I can only change one at a time. But in this case, looking for a new yogurt shop, if you look at the circle in the top right corner, the thing I want to know is, what's the impact of store location, you know, where the prospective store is going to be, whether it be South Windsor, Hartford, Manchester, Rockville, Southington, who knows where. Two, the store size, what's the impact of those two variables on my profit, right? So again, I have to collect some data, and the data that I would collect, if you look at those lines, the jaggedy lines there, not the straight red line, but those are all my store location, right? Each dot on that line it signifies a different store location. This might be Hartford, this might be South Windsor, this might be Wallingford, who knows what. And then down the bottom is the store size. So I just basically said, all right, 500 square feet is going to be store size 1. I could have written 500 there. 1,000 square feet is going to be store size 2, and 1,500 is going to be store size 3. So all I want to know is, you know, before I open another store, let's say I had these 3 open already, I want to make a conclusion based on the data on what's the smart location and the best store size, in order to, what impacts my profit the most. What are those X's that impact my Y, which is my profit? Y is a function of a bunch of X's. So this particular tool, the multivariate chart, it allows me to look at the impact of more than one variable at the same time. All right, and it's as simple as that. Any questions, thoughts? Multivariate. Again, a visual representation of the data, make the data talk a little bit. And now we're going to get into classes of distribution. I'm not going to cover, there's other ones besides the ones I'm going to present, but I think these are the ones that, you know, for green belts and most humans, these are the ones that we're going to use most often. So the way I like to think about distributions, you know, I have a whole bunch of data, and again, it doesn't talk. So some graphical, I could do some graphical way to see it, show me the data different ways. And we're going to probably stay, like I said, within these distributions. And again, if you remember that, we're going to cover these 6, all right? And 2 of them are the distributions that I would use for discrete data. And again, if you remember the difference between discrete data and continuous data, I mean, a simple way to remember is discrete data is things that I can count. Continuous data are things that I measure, right? Just to make it simple, you know, the normal distribution is the bell-shaped curve. You know, so you think about what that looks like and what kind of information I can get from it if I graph my data. We saw that with my weight, I think I did. the homework, you did a bell-shaped curve and you can kind of see where the mean is. You can kind of see my outliers, when I was fat and when I was wicked skinny, that kind of thing. So depending on what kind of data you have and what kind of problem you're trying to solve, is going to determine what kind of probability distribution I'm going to use. And they all have their own set of reasons why you use them. And remember, we used we had to get the standard deviation and sort to get the normal distribution. Well, there's all methodologies like that for each of these different types of distributions and just different ways of looking at our data. I call them probability distributions because if I have a sample and I do one of these, let's say a bell-shaped curve, the beauty of that is I can start to predict, right? And again, process control, we're thinking about two things. One, is my process capable of doing what I want it to do? And two, is it stable and predictable? Like stable and predictable, I almost think of it as the same thing, right? If it's that means it's under control. So anyway, let's go through them. So let's start with binomial distribution. And both of these are both for discrete data, right? It's used to model discrete data. It applies when the population is large and the sample size is small compared to the population. An example would be if I'm running an experiment and I'm collecting a lot of data several times in a row, and my experiment is I'm going to flip a coin 3 times. What's the likelihood of getting heads 2 times? Okay, and again, you think about the coin flip. That's definitely discrete data. Yes, no, heads, tails. It's not continuous. The Poisson is used as a distribution for defect counts and can be used as an approximation to binomial. And it's a way to see how unusual an event frequency is for a given time interval. And here's the example of like when you would consider a Poisson distribution. Let's say LeBron James, and I don't follow hockey, so you got to stay with me, but LeBron James is averaging 35 points per game, so far this season. What is the likelihood he'll score 12 points in the first quarter of his next game? So those are the kinds of problems that you would use a Poisson distribution. And we're going to get into these a little bit deeper as we get into hypothesis testing, and it'll probably make more sense. But I just wanted to give you like an overview of an example of what kind of distribution I'm looking at. And normal distribution, I think we have a pretty good understanding. I think we're pretty clear on it. Total area under the curve is equal to 1. It's shaped like a bell. It extends indefinitely in both directions and is I don't know what the hell I was thinking there. Never mind. The mean, median, and mode are the same. All processes will exhibit a normal curve shape if only pure random variation exists. Example would be if I decided I was going to, I wanted to know what's the weight of a polar bear, and obviously I can go out and I can try to track down every polar bear in the world and get their weights. And our average weight will probably be about 500 kilograms, but we know that there's been cases where there's polar bears with 750 kilograms down to 350, and those are our outliers. So if I get if I check my whole population of polar bears, then I'm probably going to get a normal bell-shaped curve or normal distribution, right? And that brings me to the student T distribution. This was like a breathtakingly important breakthrough in statistics back in the 50s, because what it does is it allows me to kind of simulate a bell-shaped curve, because you guys saw how useful a bell-shaped curve is. And I think the rule of thumb is that if my data doesn't show a normal distribution, then I can make it one by one. I can do a normalcy test. That's something you're going to see in the future that's a little bit complicated. Or I could just take more data Or if I have a small sample, but I don't want to have the outliers have such a big impact on my curve, then that's where I'd use the student T. So a smaller sample size. So let's say if I want to do a polar bear study and I wanted to kind of capture, tag, I don't know, and and then weigh polar bears. And I'm not going to do every polar bear in the world. I'm going to do some sample size. If my sample size is, over 30 polar bears, 50, 70, 90, then I'll probably approach a normal distribution in terms of the weight of the polar bear. If my sample size is less than 30, then there's a chance that I might have captured a 350 kilogram or 800 kilogram polar bear, and that's going to skew my curve, right? So it's not going to tell me enough about the data. So I use the student T, right? And it's formed by combining a standard normal random variable and a chi-square, which we get into a second. And it was a huge breakthrough in terms of understanding data that look like that in small samples. And then an F distribution is, and this isn't all that important, is used extensively to test for equality of variances. So I'm looking at two different normal populations together. So instead of having a bimodal curve where I have two modes on my curve, an F distribution is a better way of combining looking at two normal populations at the same time and drawing conclusions from both of those sets of data. In the chi-square, again, we're going to cover this as we get into the hypothesis test more. But generally, it doesn't mirror real life. It's more of a tool that we're going to use in multiple hypothesis tests. And that's kind of what I'd like you to know right now about chi-square distribution. So those are, I think that's, yeah. All right, so any questions, distributions? This is going to make, again, we're going to build on this because, again, we're going to need to pick the right distribution as we get into hypothesis tests to know which hypothesis test we're going to use over the next couple of weeks.
Could you use a Poisson distribution to check out the likelihood of like a solar eclipse or something like that happening?
Absolutely.
That would be like a good. Oh, okay.
Yeah, so it's ways to see how unusual an event frequency is for a given time interval. In other words, you look at the time between solar eclipses, how long it's been since the last one. Again, you see why it's binomial?
Yeah.
Discrete data.
Like the likelihood of like two things happening or like a very small sample.
Yep.
Gotcha.
Hey, Bill, just real quick, the student T thing there, how are you generating a normal distribution shape with a sample size that's small? Are you throwing out outliers or I mean, how are you accounting for such a small amount of data without?
Yeah, the formula, like I said, each one of these, if you remember, when you guys did the normal distribution, there was a bunch of calculations that we're going to do again today. I think it's at the top of my head, it's X is equal to my sample minus my mean divided by the standard deviation of the sample. So each of these has its own formula. In this case, it's formed by combining a standard normal random variable and a chi-square random variable. And we're going to get into what that is. So basically, it's kind of manipulating, massaging the data to kind of just give the outliers less of a score, less weight.
Okay, so you're not throwing them out. You're just
you're using the inverse basically versus just the raw number, right? So you're basically applying math to it. They don't have the same weight as they would in a normal distribution. Because I have to assume if I'm going to use a student T, that my outliers are going to badly impact what my distribution looks like. Okay. I know that going in because chances are I grabbed an outlier or two and they're going to have a lot bigger weight. If I only pick less than 30, my sample size is less than 30 than it is if it's the whole population. I'm going to get a much clearer picture with the whole population. So how do I minimize the outliers? And it's just a way of kind of just quieting down the outliers a little bit. The curve is usually a little bit broader, fatter, and the tails are a little bit, we're going to get into the tails in a second, but the tails are a little larger too, the area under the tails. But it
So
gives
there's
you,
a bell curve in T distributions.
what's that?
There's a bell curve in T distribution, just like normal.
Yeah, that's the whole idea. Because then, remember from the cool thing about the normal distribution is like, most of the time, guys, when we're collecting continuous data, our goal is to get a normal distribution, because remember the percentages that fall under the curve on both sides of the mean. It allows us to just, answer so many questions. So the student T distribution, the reason it was so important when it was invented in the 50s is because it allows me to try to do I'm not going to get great, as good as I can get up to normal, but it's going to give me, maybe point me in the right direction in terms of predicting, in terms of the next steps, things like that.
All right, so you're not throwing out the outliers, but you're kind of turning the volume down on them so they don't have the impact.
Exactly. Good. So again, I think the importance of, of the different types of distribution is that, when we get to hypothesis testing, we want to pick the right test. And that's kind of what the distribution type on the data type is, what helps us select the right test. And we're going to do we're actually going to do a hypothesis test today, like as an introduction. You'll see what I'm talking about.
Bill, one of the reasons that I asked that question, that student T seems interesting to me, because one of the difficult things at Ulbrich is we don't typically have a lot of data to work with on same items, on certain part numbers. Sometimes it's a long time between running certain jobs, and we can't collect, hundreds of data points to get a bell curve going. So something like this, without knowing a whole lot about it, seems like it could be attractive, because if we can simulate a normal distribution or a bell curve with less data, that might help in a lot of instances.
You know what? I think I just wrote down exactly what you said, Stephen. And next week I will come up with an example and take you through how to do the student T. Okay.
Oh, good. So I gave you homework.
Well, yeah, because again, I think when things like that pop into you guys' head, because there's so many, it's like, and what do you think? I hear you. That'd be very interesting, because you don't have a lot of times, you don't have months worth of data. You have last week, and you still want to be able to predict and draw conclusions. And so I'll do that for next week. Do a little bit of a student T, dog and pony kind of, where we'll take an example of some data and go through the.
Yeah, I can even try to kind of go online and dive into it a little bit and try to learn more about it too. But it seems like an interesting thing, but I don't want to take up everybody's time with it.
I think it could be useful. Yeah, I think it could be useful for the group. So, I think that's the whole value of whether you call it a green belt or any kind of learning, is like, all right, great, thank you. What do I do with it? How do I apply it? How do I use it? How do I put it in my toolbox? Thank you for that. All right, so now we're going to get into inferential statistics, which is going to be kind of an introduction to hypothesis testing too, and you'll see why. By the end of our hour. Let me get my. All right. So, statistical inference first. All right. It's the process of making inferences regarding the characteristics of an unobservable population based on the characteristics of an observed sample, right? I can't go out and get all the data. I can't get the whole population and get data. So I have to get a sample, whether it's a survey, whether it's just getting, in many cases, I can't sample every piece that comes off my line, or every pound that comes off, or every foot that comes off my coil, right? So I have to do a sample. And what I want to know is, can I make conclusions using my sample, right? That's what I'm looking to do. Can I infer certain things about the whole population based on the sample that I've pulled, right? Statistical inference is widely used since it's difficult or almost impossible to collect the entire population data. Obviously, like every polar bear, right? I have to draw the line somewhere. That would be my life's work. And statistical inference contains two elements: the inference and then the measure of validity. And I think I'm going to do an example in our math before we leave today, before we're done today. You know, kind of give you a feel for these steps. One is clearly define the objective or the research question, they call it, or the problem statement. We're going to decide whether it's evaluated by a 1 or 2-tailed test, which I'm going to show you how to do there. Formulate a null and an alternate hypothesis, right? The null hypothesis and an alternate hypothesis. Select the test distribution and a critical value of the test statistic, and then calculate a test statistic and then compare that value. And I think, you know, when we get into inferential statistics and hypothesis testing, the whole goal is, do we reject the null hypothesis? And the way I'd like you guys to think about that is, if you're on trial for robbery, you're innocent until proven guilty, right? So in this case, the null hypothesis is always going to be that no, there's no difference. No, it's not significant. And we have to prove that it is different or significant. Okay. And again, I'm going to have an example of that for you today. I think it'll help. And the outcome in statistical inference is a proposition about the population, right? And some examples might be estimating a population parameter, identifying an interval or a region where the true population parameter would fall with some certainty, deciding whether to reject the hypothesis, which is what we're going to do with it, made on characters based on characteristics on the population of interest, making predictions, or clustering or partitioning data in different groups. Okay. And let's talk a little bit about sampling. Because again, you know, most of the time, like you said, you're not gonna sample every foot of coil. You know, we have to take samples. In statistics, population is the entire set of objects or observations in which we're interested in drawing conclusions or making generalizations. And sampling is the process of selecting a subset of the observations within a population is referred. So I think, you know, the key thing here is that, does my sample represent my population? You know, and that's kind of what a lot of this, what we're talking about is, what's what we're trying to figure out. You know, is it representative? And if it is, can we predict based on what we have for a sample? The advantages are, obviously, it's impossible or impractical to collect the data of an entire population. It could be a lifetime, like if I wanted to know the weight of polar bears, high cost, time consuming, availability to historical records, dynamic nature of the population. And the advantages of sampling is lower cost, faster data collection, easy to manipulate. So uses of samples, there's two major uses. And when we're taking samples, and one is estimating the population parameters using sample statistics, and two, hypothesis testing, which is testing a statement about the population characteristics using sample data. And the basic sampling strategies, we're going to go touch on these quickly, each one. Simple random sampling, matched random sampling, stratified sampling, systematic, proportional to size sampling, and cluster sampling. It's almost like, remember Steve Martin years ago, he used to say, those French, they have a word for everything. Well, it's kind of the same thing with these statisticians. you kind of take these things and dive in with an electron microscope. So there's, what is there, 3, 4, 6 different sampling strategies. So simple random is just exactly what it sounds like, right? Each item has an equal chance of being picked. There's no bias. We just grab them at random, and it's the basic sampling strategy that I thought it was the only one until I got my green and black belt 20 years ago. But I guess it's not. And there's match random, where samples are randomly selected in pairs, each of which has the same attribute. And the examples there are, let's say researchers are interested in understanding the weight of twins at birth, for example. Or researchers are interested in understanding the patient's blood pressure before and after taking some medicine. So it's selecting, still random, but in pairs. And then stratified sampling, it's into distinct and independent categories. An individual category can be considered as a subpopulation. These samples are randomly selected in each category. Let's go to the example. A fruit store wants to measure the quality of all their oranges. They decide to use stratified sampling by region to collect sample data. Since about 40% of the oranges are from California, then 40% of the sample is selected from the California oranges. And then, maybe it's 30% from Florida or whatever. So it requires advanced knowledge of the population characteristics. And the categories can be, again, I know I'm skipping back up, but gender, region, income, travel. So stratified sampling. And then systematic sampling, regular intervals based on an ordered list where items in the population are arranged according to a certain criteria. Systematic sampling has a random start, and then every Xth item is selected going forward. For example, we're going to sample every 5th unit produced on the production line. What do they call that in quality, Steve? An AQL, right? Daniel? Where we're going to do, out of a batch of 1,000, we're going to do 20, and we're going to do every 5th one, or that's systematic sampling.
Yeah, at a company I used to work for, we actually did it every hour. We did it by time.
Okay, by time too.
We would take a sample and like check it.
Yep, good. That's another good example. It's not random, just going up to the line and picking one off and testing it. And then cluster sampling, it's a sampling method where samples are only selected from certain clusters or groups. It reduces the cost and time spent on sampling, but bears the risk that the selected clusters are biased. And an example is selecting samples from the region where researchers are located so that the cost and time spent on traveling is reduced. All right. And sample size is important. And again, these statisticians have a tool for everything, kind of like the French have a word for everything. You're going to see some formulas on what's my right sample size. It's a critical element that can influence the results of inference, of knowing what to do next or predicting. The smaller the size, the higher the risk that the sample statistic won't reflect the true population parameter. And the greater the sample size, the more time and money we will spend on collecting samples. So for continuous data, that again is data that we can measure, there's an equation for the sample size of continuous data. So the capability analysis is a minimum of 30 samples. So number of samples is n naught, and that's equal to the z-score. So again, we got to go to a table, get a z-score, and it's kind of an estimated standard deviation, and then desired margin of error, which you can make up, what do we want to see, our confidence level. Just to let you know, all I'm saying here is, listen, if you really want to get statistical and play with the big boys, they do have a formula for not only continuous data. Again, here's another one. Here's an example. But discrete data too. So there's a separate formula for how big should my sample be. All right. And we're going to get into reading tables in a future lecture, z-score and all that. If calculated sample size exceeds 5% of the population, then discount using the following equation. So yeah, they turn it into a science. Sampling errors. There's a couple types. One is a random sampling error, and that's random variation due to observations being selected randomly. It's inherent in the sampling process and beyond one's control. I just might have picked a 350 kilogram polar bear, you know, or I might have got a family of, or an area where they're all 300 pounds, or 300 kilograms. And there's also selection bias, which is non-random variation due to inadequate design of sampling. It can be improved by adjusting the sampling size and sampling strategy. The science of sampling. Now, into the fun part. I'm just gonna, again, we're just today, probably another 10 slides, then I'm gonna go over to our math practice and actually try to do some messing around with this stuff. So some general concepts and goals of hypothesis testing. So a hypothesis test is a statistical method in which a specific hypothesis is formulated about a population, and then we have to decide whether to reject the hypothesis, and it's based on sample data, right? So I have a sample, and I want to make a conclusion. What's our next step? You know, and this is where the hypothesis testing comes in. And there's really two themes that you're going to hear over and over, because a hypothesis is always done in pairs. One is the null hypothesis, H naught, and an alternate hypothesis, which is HA, alternative hypothesis. The hypothesis testing tries to answer whether there's a difference between different groups or there is some change occurring. And some examples are the average SAT scores of graduates from high school A and B the same? Now, I'm not going to go and I may not go and check every score of every kid. I may sample high school A and sample B. Is the error rate of one group of operators higher than that of another group? Are there any non-random causes influencing the height of kids in one state? These are the types of questions why I would do hypothesis testing. So let's talk a little bit more about the null and alternative. So the null hypothesis is always where we start. That's the innocent until proven guilty kind of thinking. So we always start with a null hypothesis. We start with a problem statement, and then the first thing we're going to do is kind of come up with a statement that is our null hypothesis. I'm going to give you an example of that when we get in our math practice. Basically, it states that there's no difference in the measurement or different groups. There's no changes. Sample observations result from random chance. We're saying everything's fine. You're innocent, right? The alternative hypothesis is going to state that yes, that there's a difference in the measurement of different groups. Some changes have occurred. Sample observations are affected by non-random causes. All right, that's the difference. And again, in hypothesis testing, all we're always trying to do is disprove the null hypothesis. That's the goal of hypothesis testing.
So can it be like the scrap rate between operators, like the difference in the scrap rate or something like that?
Yeah, so right away we're going to say, you know what, there's no difference in the scrap rate. And then we got to prove it. And, it could be easy to prove, it could be, but you look at it over time, you're collecting a bunch of data, but the null is always going to be, there's no difference. Okay, that's what I'd like you to remember. And you're going to, I think that's a good example, Daniel, and you'll see it in the little exercise we're going to do shortly. Okay, so it starts with problem statement, or some people call it a research question. And then based on that research question, I'm going to write out first my null hypothesis, which is going to be there's no difference, and then 2, there is a difference. So if we're going to do a hypothesis test on the operators, like you said, Daniel, then my null hypothesis is going to be there's no difference. It might be very easy just looking at the data. I may not need to do any hypothesis testing. It could be night and day. All right. So conclusions. 2 possible conclusions of hypothesis testing. 1, reject the null. In other words, convict. Innocent until proven guilty. My only objective is they're innocent. I need to figure out how to make them guilty. And then the other possible conclusion is I fail to reject or I quit. All right. When there's enough evidence based on the sample information to prove the alternative hypothesis, then we can reject the null. And there's a mathematical way that we can do that. All right, and that's what I'm going to show you. And when there is not enough evidence, or the sample information is not sufficiently persuasive, then we fail to reject the null hypothesis. Right? And failing to reject means they go free. All right. So let's talk just quickly about significance, practical versus statistical. Practical significance is when it's large enough to make a practical difference. All right, like looking at those two sets of data on the operators that Daniel Mendoza just brought up. I mean, it's practically significant to know, that it's night and day. I could look at the data quickly and know that there's an issue. A difference between groups that's statistically significant might not be large enough to be practically significant. Okay, it might be just cutting hairs. In some business situations, statistical differences can have little or no meaning because the difference is not large enough to be practical for a business to act on. And again, statistical significance, it's unlikely that the difference occurred by pure chance, given a predetermined probability threshold. Statistical significance indicates there are some non-random factors causing the result to take place, special causes, which we're going to cover when we get into control. The statistical significance level in hypothesis testing indicates the amount of evidence that is sufficiently persuasive to prove that a difference between groups exists, not due to random chance alone. And probability refers to the likelihood, the chance or possibility of an occurrence. The probability of any event lies between 0 and 1, and the sum of all the probabilities of all possible events in a sample space is 100%. The probability is always a ratio. And I'm going to give you an example of a die, of tossing a die in a minute. The ratio of the chances of an event success versus the total number of ways an event can occur, success and failure. So this is a probability. Here's an example. A die has 6 sides. So I basically have 6 samples, right? Every time that I roll my die, each face is unique. Each time a die is rolled, there's a 1 in 6 chance that it'll land on any specific number. So I can state that as 1 out of 6, or 1/6, or 0.1667. So the odds of getting any one particular, getting a 2 when I roll it, is about 16.67%. Not about, it's 16.67%. So now I ask the question, well, what's the probability of me spinning 5 2s in a row, or 2 1s or 3s or whatever? Let's say 1s in a row. Yeah, 5 1s in a row. So P, the probability of doing it once is 16.67%, which is 0.1667. And if I do that 5 times, I multiply 0.1667 times 5. So the odds, I have 1.3 chances out of 1,000 that I'm going to get 5 1s in a row by rolling the dice. That's probability. Okay. Calculated probability allows the establishment of acceptable risk, thus gambling. And the p-value, the differences between observed data and claims made under the null hypothesis may be real or due to chance. The p-value is the probability of those differences occurring solely due to chance, random. And then the alpha level, the level of significance of a test, represents the threshold against which p-values are measured. And that, what I mean by alpha level is if, what we're going to talk about today is what are our rejection areas on a bell-shaped curve, for example? Like if a piece of data falls outside into those outliers, what's an outlier? That's what an alpha level means. So these statisticians, they not only have a tool for everything, but they have a lot of different ways of calling the same thing. So alpha level can be confidence level, it could be rejection region, and we're going to talk about that in a second when we get into the regular problem. And the null hypothesis is rejected if the p-value is less than the alpha level. All right, and it's and commonly used levels are 5, 10, and 1%. So what I mean by that is and you could set those, right? If I have a piece of data and I'm saying, boy, is this thing really unusual? Is this too far off the mean for me to, or is it an outlier, right? Well, I can set my confidence level, my rejection region on the curve by saying I want to have a 95% confidence level, or I want to be able to make that decision with 90% or by 99%. And I could make that call, right? But I have to do it before I actually do the test, before I flip the coin or whatever, right? I want to set those first. So risk, alpha and beta. This is kind of simple. And again, remember as we go through this, that the goal of hypothesis testing is to reject the null hypothesis. So a type 1 error is called a false positive, right? A false alarm or alpha error. Type 1 error are associated with the risk of accepting a false positive. And it occurs when we think there's a difference between groups, but in fact there isn't, okay? And an example of that would be telling a patient he is sick, and in fact he is not. Alpha indicates the probability of making a type 1 error. It ranges from 0 to 1, right? So an alpha risk is the risk of making a type 1 error. 5% is the most commonly used alpha. And you know, so again, it's going to make a little bit more sense, I think, as we get into our example. You know, so we want to work at a 95% confidence level. So 100% minus that alpha is the confidence level, which is used to calculate the confidence interval. So when I'm looking at a piece of data and trying to understand if this is weird, then all I'm saying is I want to have 95% confidence in this. And that's what confidence interval levels or intervals are. And that's all that alpha means too. So when making a decision on whether to reject the null, we compare the p-value against alpha. All right, and a p-value, we're going to calculate that out today. If the p-value is smaller than the alpha, we reject the null. If the p-value is greater than the alpha, then we reject it. We fail to reject the null. And to reduce the alpha risk, we decrease the alpha value to which the p-value is compared. So in other words, we make our rejection regions larger, I'm sorry. A type 2 error, on the other hand, is also called a false negative, an oversight, or a beta error. Type 2 error is associated with the risk of accepting false negatives. It occurs when we feel there's not any difference between groups when in fact there is. It's telling a patient he is not sick, and in fact he is. Right? Beta indicates the probability of making a type 2 error, and it ranges from 0 to 1. Same thinking, you know, with this type of an error as we did with alpha. It's the beta risk is the risk of making a type 2 error. 10% is the most commonly used beta. So 90% confidence level. 100 minus beta is called power, which denotes the probability of selecting a difference between the groups when in fact the difference truly exists. You know, so if I'm working at a 90% confidence level, then the power would be 10. So to reduce the beta risk, we increase the sample size. When holding other factors constant, beta is inversely related to alpha. All right, so that's that. And the confidence interval, which we just kind of talked about, is the interval where the true population parameter would fall within a certain confidence level. So think again of the bell-shaped curve. A 95% confidence interval indicates the population parameter would fall in that region in 95% of the time, or we are 95% confident that the population parameter would fall in that region. All right, and 95% is the most commonly used confidence level. And that's exactly what we're going to do today. So let me just finish this up. The width of a confidence interval depends on the confidence level, the sample size, and the variability in the data. The higher the confidence level, the wider the confidence interval. The smaller the sample size, the wider the confidence interval, and the more variability, the wider the confidence interval. Here's just a quick, this is easy, so bell-shaped curve, our rejection region, when we're saying, hey, this data, this information falls outside, it's a special cause. It would be when it falls into this region, this darkened region here, right? And all we're saying is, at 90%, the region might be here, on the line, the white vertical line before that darkened region starts. So we're just kind of 95%, 99%, we're making that just a harder test. So I'm going to stop here. Everybody catch the breath a sec. I'm going to stop sharing. Whew. Any questions, thoughts? Are we okay? A lot of information. Let's get into our math practice for a second. See if this helps. Okay, everybody see that? All right. The one thing I miss about my, I had a tablet that you can write on. I forget what they call them. Anyway, the battery blew up, so I had to get a regular PC. I can't write on it now. Right now, I got to figure. I have to get another one. Anyway, so let's take what we just talked about and let's apply it to a problem. All right. So here's the problem. I thought, because it's wintertime, I'd throw this picture of a beach up there. The temperature last July 15th was 94 degrees. Was that day's temperature significantly different than the average for the month of July over the last 100 years? All right, that's the question. Was the temperature on July 15th statistically significantly different than the average for the month of July? So the data set you can see here on day and temperature. You can see I highlighted all that data. Basically, it's the average temperature for each day through the month of July over the last 100 years. So if you remember, there's a bunch of steps we're going to go through. There's 6 steps in terms of understanding whether that day, the 15th, was out of whack or not. Right. So the first thing is my research statement, and the research statement, you're looking at it. The temperature last July was 9. Was that day significantly different than the average for the month of July? All right. So if I'm going to take this bell-shaped curve. This bell-shaped curve is the data. Is this month July's temperatures over the last 100 years? And I'm going to lay it over my scribblings like that. All right. So you can see from my data down the bottom that the mean for July is 87.5 degrees Fahrenheit, and my standard deviation is 3.5 degrees. So there's my bell-shaped curve. My mean is at 87.5. Now, if you look to the right and the left, the colored areas, the curve, that's my rejection region. What I'm thinking about is 94 out of whack. All right. So starting with my research statement, my first thing to do is I have to come up with a null hypothesis. And my null hypothesis is going to be what, based on this research question? Anybody?
That it's not significantly different.
Bingo. Null hypothesis. Just think, no, there's no difference between July 15th and the average. Okay. No statistical difference. So that'd be my null hypothesis, that no, there's no significant difference of July 15th. And what would my alternative hypothesis be?
There is a difference.
Hey, you guys pretty good, right? Exactly. So that's my first step. All right. And it's a pretty simple application of this thinking, but so bear with me. We got a research question. We come up with a statement, a null hypothesis, and then alternative hypothesis. And then the next step is is I got to determine whether this is a one-tail or a two-tail test, okay? And the way I determine that is if this question was that day's temperature significantly hotter than the average for the month of July, then that would be a one-tail test because all I'd be looking at is the right side of this curve, right? I just want to know, is it hotter? Or a one-tail test might be, was a particular piece of data cooler than normal, right? All I'm asking here is there a difference? So when you see the word different in your research statement, your hypothesis, your null hypothesis statement, it means we're going to do a two-tail test. All right, and that matters I'll explain why in a second. All right, everybody with me so far?
Yeah, I like that example that you just gave.
Okay. All right, so now I have, now before I go too far and trying to understand whether 94 degrees is significantly different, than the average for the month of July. Is it an unusual day? Is it out of whack? I have to kind of set the limits on, like, what am I going to, like, what region, like, where am I going to say, if it's beyond this confidence level, then we're going to reject the null hypothesis. All right. The null hypothesis, again, is there's no difference. So there's a couple ways that I can determine or define where my rejection region is on the curve. You see, you guys see the purple, I filled it in over here. This is the rejection region. Anything outside of here, any data point that comes out here, I'm going to treat it like a 200 kilogram polar bear. And over here, it's going to be an 800 pound polar bear, right? So in other words, does 94 fall outside the rejection region? And if it does, then I'm not going to be able to reject the null hypothesis. No, I'm sorry, I will be able to, right? Once it gets the rejection region, that's why I call it a rejection region, because some people call it alpha and there's other things you can call it. So if my data falls outside that level, so how do I get that level? There's a couple ways. One, if you remember, let's say I wanted to do a 90% confidence level. I said, you know what? I want to be confident 90% that 94 falls outside of a statistically different. Largely what I'm going to do is take that 10%. So 100 minus 90, 10%. And because I have a two-tailed test, I'm going to put 5 degrees to the right, 5 degrees to the left to make the 10. If it was a 95% level, then I'm going to do a 2.5. And my rejection region is going to be 2.5 degrees, and the same thing on the other side. Like I said, statisticians, they have a word for everything and a tool for everything. There's also something we call a Z-table, where if I'm saying for a 95% confidence level, I can go into a table that tells me that anything over 1.96 on each side degrees is going to be my rejection region. There's actually a table that for a 95% rejection level. Okay. So I have my rejection region set up. And now I'm going to develop my test statistic. And my test statistic is my Z-score, which is going to be my X, which is going to be 94 degrees, minus my mu, which is the mean, 87.5, divided by my standard deviation, which is going to be 3.5. And what I'm going to get there, if I do the math, is 1.857 for a Z-score. And now I'm going to take my 1.857, I'm going to put it into this chart. Now, where would that fall? So let's say this is 0, right? This is an 87.5. This is our mean. This is 0, and they got sigmas on each side. Where would that test statistic fall, that 1.857? Would it be before or after the 1.96, the rejection region?
Before.
Right? It'd fall probably between, right? I don't know if you guys can see.
I get a question. What was the mu again?
The mu is the
What
Right here?
value?
yeah, the
Yeah.
average.
Oh, it's
That-
just average.
Yeah, it's just the average of the population. So if you
Okay.
average these out. Yeah, I think I didn't go through, you know, how I got this. Largely, it was like, here's the data. Remember, we have to sort it, and then we have to do the formula for normal distribution. And then I drew the graph. It's not a really pretty bell-shaped curve, but it works. But yeah, the mu is going to be the average of the population. So it's my sample, 94 minus the mu or the average. I'm just going to say average. It's almost like when people get pissed off at me because I use Japanese terms. Yeah, we're going to use, why don't we stop using these signals? Yeah, so basically you're right, Daniel, or whoever said it. My test statistic falls in between the 87.5 and my rejection region. So what do I do now, right? If I failed to, now I failed to reject my null hypothesis because it didn't fall into the rejection region. All right. And that's the only conclusion I can make doing this test. All right. Is that no, July 15th is not significantly different than the average for the month of July for the last 100 years. All right. So I think I got to, we got to talk about, alpha and rejection regions, confidence levels. Just because again, we're gonna go after this a little bit more, as we get into more hypothesis testing and different types. Okay. Any questions about the basics, how that works? 1, research question. 2, a null hypothesis, an alternative hypothesis. Is it a 1 or 2 tail test? Come up with a test statistic and plug it into my graph and see where it falls.
Bill, what's the sort? I got confused now.
Oh, remember when we did when I asked you guys the homework to do a bell-shaped curve of my weight?
Yeah.
Yeah. So basically, in order to remember, because we wanted to be able to make that's how it's one of the steps to do a bell-shaped curve, Sergio.
Right, but we didn't define any period here.
No, it's basically, this is going to be all the data for July, just sorted from the coolest day to the hottest day. And that's so I can get a normal distribution. I think we did the same thing with my weight, didn't we? It went from skinniest to fattest. And when you guys did the homework, that's all. It's a way that I can get a bell-shaped curve, in Excel.
So it's just to get the arc that way.
Yeah, exactly.
Well, I
You remember that,
understand,
Sergio?
but if July 15th was 94 degrees,
Yep.
why the next column is 88?
Oh, no, because the next column, I'm just sorting all the data that's in column B. I'm sorting it from smallest to biggest, so I can do a normal distribution curve.
Okay, yeah, sure.
Did I answer it?
Yeah.
You get a sense of feel for it, guys, in terms of we're kind of dipping our toe into the analyze phase.
Yeah.
The data just lays there. It doesn't do anything. Like you look at it, okay, that's data. This is what this is all about. It's like different ways of making it talk to us. So I'll have a recording for you. I'll get the homework off to Roy and the video off to Roy and Andrew. And I hope it was good. I was excited, but I stumbled a lot today. I apologize. Any questions?
Yeah, how are we going to use this enough to keep control of it?
What's
You know
that?
what I mean? This is the kind of thing, if you don't do this on a regular basis going forward from here, you're
Gonna forget it. Great.
it's
Yeah.
not the kind of thing you can pull out once a year and have any kind of command of it, I'm sure.
I think, because I'm the oldest guy here by a lot now. I'm just 60. Like if I read a book, I get one thing or two things, maybe a movie, 1 or 2 things. So it's like, I think, like you said, student T, Bing, that's what I would write, because that might be something that and I think that's the approach, because it's just, imagine doing this thing 4 days in a row, 8, like you probably did, Brendan. When you got your green belt, what was it?
Well, it was through a creative inquiry, so it was over a couple months, but
Oh, okay.
Yeah.
but normally it's like 4 days, full days, exam on Friday. You know, Monday through Thursday, just 1,600 PowerPoints. And it's like drinking from a fire hose. You just, you know, you want to forget it by the time you get home. You know, so I think even week to week, you know, as you pick up things, and I at Elbrick, I want to do a Six Sigma 4A3 kind of a, like an overview of some tools that people may use. You know, 2 or 3 things you might use in the current condition, in the root cause, in the because I agree with you. It's
No, don't misunderstand me. I wasn't complaining or
no, I know.
asking you to tell me how to do that. I'm saying I'm going to have to figure out a way to incorporate this into what I'm doing, or it's not going to be usable. You know what I mean?
Yeah.
Using some of it at least on a regular basis is going to be important. Is what I was getting at.
Well, let me ask you this question. I'm going to ask Brendan, how much do you use? What parts of do you use? You know, of your training?
Well, now I feel like a lot of the technology will do a lot of the visualization for you. So it was interesting when you're talking about sampling, because now I feel like with some of the analytics tools, they'll take an entire amount of data and they'll visualize that data for you. But it's important to understand the inputs to create that visual. So rather than just looking at it and taking it for what it is, understanding the statistics behind it, not in depth to be able to create it, but to just digest it. So I feel like the tools are kind of presenting it for you, so you don't have to do all that manipulation yourself, but still to then digest it, it's helpful to have the statistic background.
Yeah. Otherwise, you don't know what's significant or not, or
You can look at a bell curve.
what's happening in the background. Then
Yeah, it's a bell curve, but if you don't know what a bell curve is and what it presents, then it's not too useful to you.
Yeah, I think that the trick is, you know, because if you look at Sean and Sergio, for example, you know, versus Brendan versus Daniel and Steven, right here, there's probably 3 different possible applications of some of this, you know, in terms of what your roles, your job, your responsibility, you know. So, and the problem is when you get you a green belt, you know, here it is, figure it out, have at it. So hopefully, you know, like things like when Steven, you said, hey, tell me more about the tea. That's kind of, I think, what we're after. You know, what can I dig in and go a little bit more, you know, more depth on, because it's just drinking from a fire hose. But I'm hoping that, you know, it makes sense at least to you. You know.
Another good example is now with Excel, you can put equals z-score and it'll take the data and it'll calculate a z-score. You don't necessarily know how to calculate that z-score. You have to know what to do with the z-score.
Exactly, but the logic of understanding what a z-score is and how, you know, like how does it all fit together? I think it's good to know.
I've totally forgotten a lot of this, but I'm realizing I'm using it just in different applications.
All right, no homework. Well, I'll see you guys next week. Thank you so much. Hope it wasn't too bad.
Thank you, Bill.
Good
Great
week.
night.
Thank you.
Yeah.
Thanks, Bill.
Have a good weekend.
Correct.